Hello, welcome to Department of Collegiate and Technical Education. In this session, that is session 3 of Unit 1 of Digital Electronics subject, I am dealing with applications of multiplexers. In this session, I am going to cover applications of multiplexers, implementation of Boolean functions, implementation of logic gates. In the last class, we studied about multiplexer. Multiplexer is commonly known as MUX. It is a digital switch or it is a data selector, and it can also be called as data router. It is commonly known as many to one device. It has multiple inputs and single output, and therefore it is called as multiple input single output device. In multiplexer, there are n data inputs, one output, and m select inputs. It is a digital circuit which selects one of the n data inputs and routes it to the output. So therefore, it is called as data selector or data router. The select lines determine which input is to be connected to the output. If number of select inputs are n, then maximum number of inputs is 2 to the power of n. Then the multiplexer is 2 to the power of n is to 1 mux, or 2 to the power of n to 1 mux, or 2 to the power of n by 1 mux. So here we have the multiplexer orders such as 2:1 mux, 4:1 mux, 8:1 mux, etc. So in 2:1 mux we have two input lines, one output line and one select input. And in 4:1 mux we have four input lines, one output and two select inputs. And in 8:1 mux we have eight input lines, three select inputs and one output. So now let me start with today's topic. So in this session, I am dealing with applications of multiplexer. Multiplexer can be used for data selection, data routing, waveform generation, parallel to serial conversion, frequency multiplexing system, logic function generation, and it finds the main application in communication. Other than these applications, multiplexer can also be used for the implementation of Boolean functions and logic gates. See, first coming to the implementation of Boolean function. So if the Boolean expression is given, in the last session, I have shown you how to implement using logic gates if the Boolean expression is given. So now the same expressions can be implemented using a single mux. So now we'll study these things. That means implementation of Boolean function. Okay, in this method, n variable Boolean function can be implemented using 2 to the power of n to 1 mux. See, n variable Boolean function means if we are that means the number of variables which we use in the Boolean function. See, for example, if I am using a, b and c as the variables in the Boolean expression, then it is called as three variable Boolean function, and it is implemented using 8:1 mux. If I am using a, b, c, d as the variables, that means four variables, then it can be implemented using 2 to the power of 4, that means 16:1 1 mux. So in general, what we say is n variable Boolean function can be implemented using 2 to the power of n is to 1 mux. The minterms present in the Boolean function are made equal to logic 1 state, and the remaining minterms are made equal to logic 0. Let me consider one example. F of a comma b comma c is equal to summation 2 comma 4 comma 7. Actually, it represents Boolean expression. 2, 4, 7, they represent the minterm values. So what is minterm? Minterm is nothing but product term. That means it is a product of variables and their complements. See here, 2 is the minterm value. It can be written in Boolean form as a bar, b, c bar. And 4 is written as a, b bar, c bar. And 7 is written as a, b, c. So these are the minterms, but their values are 2, 4 and 7. So in this expression, the minterm values are specified, and the same expression can be written using Boolean variables. See, in this slide, I have shown the Boolean expression. So the same Boolean expression, that means f of a comma b comma c is equal to summation 2 comma 4 comma 7 can be written using the variables as f of a comma b comma c is equal to a bar b c bar plus a b bar c bar plus a b c. So here a bar b c bar represents the represents 2, a, B bar, C bar represents 4, A, B, C represents 7. See, now first we have to construct the truth table. Here, since we have used 3 variable expression, so it consists of 8 minterm values, that is 0 to 7. And truth table entries, there are 8 truth table entries starting from 0, 0, 0 to 1, 1, 1. And now we have to write the output values. See here, in some entries I have written 0 and in some entries I have written 1. So if the Boolean, that means minterm is present in the expression, that entry should be made as 1. If the minterm is absent in the expression, then that entry should be made as 0. See, in this example, 2, 4 and 7 are present. So therefore, for 2, 4 and 7, we have to write the entries as 1, logic 1. And the remaining minterms, that means 0, 1, 3, 5, 6, they are written as 0. So that means the minterms present in the expression are written as logic 1, and the minterms absent in the logic expression are written as 0. See here. Next, for implementation of this expression using mux, we have to consider 8 is to 1 mux. So why 8 is to 1 mux means it is a 3 variable expression. So if there are 3 variables means we have to consider 2 to the power of 3 is to 1 mux. That means 8 is to 1 mux. So therefore we have to use 8 is to 1 mux. So in this 8 is to 1 mux, there are 8 input lines: I0, I1, I2, I3, I4, I5, I6 and I7. And there are 3 select inputs: A, B, actually S2, S1 and S0, and these three select inputs are connected to the variables A, B, and C. So now the input lines are connected such that, so here if the minterm is present, okay, then the input line corresponding to that minterm is made, or it is connected to logic 1. If minterm is absent in the logic expression, then the corresponding input line is connected to logic 0 or ground. So in this example, minterm 2, 4 and 7 are present. So therefore, the input lines I2, I4 and I7 are connected to logic 1 or VCC, and the minterms 0, 1, 3, 5, 6 are absent. So therefore, the input lines I0, I1, I3, I5, I6 are connected to logic 0 or ground. So this completes the implementation of Boolean function. So that means for the given expression, we have implemented the X circuit using 8:1 mux. See, in this way, if any Boolean expression, if it contains two variables, then we have to implement that using 4:1 mux. If any expression, if it contains the four variables, then we have to implement it using 16:1 mux. So here, order of the mux is dependent on the number of variables used in the expression. See, in this method, see actually there are three drawbacks. Okay, so first thing here, since order of the mux is high, then number of that means propagation delay is more. Then since there are 8 input lines, then it increases the complexity. And also since order of the mux is high, means the cost will be more. Okay, so these are some drawbacks of this method. So there is a better technique where the same Boolean expression can be implemented using lower order mux. That means here we are using 8:1 mux. The same thing can be implemented using 4:1 mux. Okay, so this is the second method where I can use the lower order mux for the same Boolean expression. See here, actually first thing is the total number of variables used in the expression is written in n plus 1 form. For example, if there are three variables, then here we'll write it as 2 plus 1, 3 as 2 plus 1. If there are four variables, means here we'll write it as 3 plus 1. 4 is equal to 3 plus 1. So in this method, we'll take like this. Okay. So Boolean function with n plus 1 variables is implemented using 2 to the power of n is to 1 mux. Actually, that for example, if three variable expression is there, then we have to use 2 to the power of 2 is to 1 mux. That means 4 is to 1 mux. But in the previous method, we used 8 is to 1 mux for designing of the same expression. So here we have reduced the order of the mux. And here totally there are n plus 1 variables. Out of these n plus 1 variables, n variables are connected to select input, and the left out variable is used as input line. So if we are using three variable expression, then out of three variables, one variable is used as input and the remaining two variables are used as select inputs. This can be illustrated by taking the same previous example, that is f of a comma b comma c is equal to summation 2 comma 4 comma 7 is equal to a bar b c bar plus a b bar c bar plus a b c. So 2 plus 1 variables require 2 to the power of 2 is to 1 mux, that is 4 is to 1 mux. That means we can implement the same expression by using 4 is to 1 mux. And already you know 4 is to 1 mux has 4 input lines, that is I0, I1, I2, I3, two select inputs S1 and S2 and only one output line. Coming to the steps of this implementation of the Boolean function. So first step is we have to draw the truth table for the given number of variable function. So already you know how to draw the how to write the truth table. So it is same as the previous thing. So that means if it is a three variable expression, the truth table contains totally 8 entries. If there are two variables and truth table contains only 4 entries. Okay, so first we have to see the number of variables, and depending on that we have to construct the truth table. See here. So totally there are three variables A, B, C, and it has totally 8 entries, 0 to 7. Here out of three variables, one variable is taken as input variable and the remaining variables are connected to select inputs. So here I have used A, B and C as the variables, and out of these three variables, B and C are connected to select inputs and A is taken as input variable. So in the next step, we have to form the matrix. Already you know what is matrix. Matrix consists of rows and columns. So here in this matrix, each box represents a minterm with input lines I0, I1, I2 as the columns. So in this matrix, actually matrix means it consists of rows and columns, and columns are represented with input lines. So in the column we'll take the values I0, I1, I2 and I3, and input variable and its complement as the row. So that means is actually here it consists of two rows. One row is represented as A bar, and in the second row there we take A as the variable. See here for construction of the matrix. So here I have taken four columns I0, I1, I2 and I3, two rows A bar and A. So for the formation of matrix, we have to take the input lines as the columns and the variable input variable and its complement form as the rows. So now we have to fill the boxes of the matrix. So for that, first we have to consider the first row. First row is with A bar. Okay, so now we have to fill the, see, for filling the first row is filled with the minterm values whose input variable value is 0. So that means where A is 0. So those minterm values will be filled in the first row. So here A is 0 for minterm 0, A is 0 for minterm 1, A is 0 for minterm 2, and A is 0 for minterm 3. So therefore, in the first row, we'll fill with 0, 1, 2, and 3. And second row is filled with the minterm values where A is equal to 1. So that means the remaining minterms 4 for 4, 5, 6 and 7, A is equal to 1. So therefore second row is filled with 4, 5, 6 and 7. So that means now the filling of the boxes is over. Okay. So next we have to highlight the boxes. So if the minterm is present in the Boolean expression, then the corresponding box is highlighted. See, for example, in this example, the minterms 2, 4 and 7 are present. So therefore, we'll highlight these values. So that means 2 is highlighted, 4 is highlighted and 7 is highlighted. So you can highlight the boxes by using circles, or simply we can say it is highlighted. So after highlighting the minterms present in the Boolean expression, then each column is inspected individually. If neither minterms of a certain column is highlighted, a 0 is written below that. If both are highlighted, a 1 is written below that. If only one is highlighted, the corresponding variable is written. See here. In the first column, 4 is highlighted. So therefore, the variable corresponding to that 4 is written below that. See, in the first column, 0 is not highlighted. So we are not considering A bar. But 4 is highlighted. Therefore, corresponding variable for that 4 is A. So therefore, below that we'll write A. And coming to the second column, in that no entry is highlighted. Either one is neither one is highlighted nor 5 is highlighted. So therefore below that we will write 0. In the third column, 2 is highlighted, 6 is not highlighted. The corresponding variable for 2 is A bar. So therefore below that we will write A bar. And in the last column, 3 is not highlighted, but 7 is highlighted, and the corresponding variable for 7 is A. So therefore, we'll write A. So now we have to implement this using mux. So already I told you that we have to consider 4:1 mux for the implementation of this given Boolean expression. So 4:1 mux has I0, I1, I2 and I3 as the inputs, S1 and S0 as the select inputs, and F is the output. So already in the first step, I told you that out of three variables, one variable is taken as input variable and the remaining variables are taken as output they are connected to select inputs. So here B and C are connected to select inputs directly, and now we have four input lines. These four input lines are to be connected to the input, that means input variable A. So how to connect means, here we have generated the table. So in that table for I0 it has come as A, for I1 it has come as 0, for I2 A bar, and for I3 A. So therefore I0 is connected to the variable A, then I1 is connected to logic 0 or it can be grounded. I2 is connected to A bar. So therefore, it is connected to A through NOT gate. And I3 is connected to A. So now the implementation is complete. So here, so once again, I'll explain. So that means for Boolean, for implementation of this three variable Boolean function, we have to use 4:1 mux. So that means in previous method, I have used 8:1 mux, but the same expression can be implemented using 4:1 mux, and it is a better technique compared to the previous one. Why means it reduces the complexity, it reduces the order of the mux, therefore cost will be less and propagation delay is less. So therefore we say that it is a better technique. See, the same method can be used for the implementation of logic gates. So already you know what is logic gate and which are the different types of logic gates. So there are actually 7 logic gates, and these 7 logic gates are divided into 3 groups: basic gates, universal gates, and derived gates, or not and gates. They come under basic gate, or they are the basic gates. NAND and NOR are the universal gates, and XOR and XNOR are the derived gates. So now these 7 gates can be implemented using logic, that means mux multiplexer. First, coming to the OR gate. Okay, first I'll define what is OR gate. See, OR gate is the logic circuit in which output is 1 if any one input is 1, or all of its inputs are 1. Or in another way, I can say that output is 0 if all of its inputs are at logic 0. So it can be written in the truth table. By that means here, for OR, here I am using 2 input OR gate. So therefore I have to use 2 variables A and B for the inputs, and output is Q. See here, since there are 2 variables, it consists of 4 entries, and according to the definition, okay, so if all the inputs are 0, output is 0. If any one input or all the inputs are 1, output is 1. So this is the truth table of OR gate. So now we have to implement this using mux. See, mux, here I can use 2:1 mux for the implementation of logic gate, and 2:1 mux has 2 input lines and 1 select input and 1 output. So here the 2 inputs are I0 and I1, select line is S, and output is F. See now, I have to first construct the table. So for that we have to form the matrix. Uh, so already I have explained the steps and I have shown the example while implementing the Boolean expression. The same thing has to be reproduced here. But here we are using 2:1 mux. So therefore it has only 2 columns, that is which represent the 2 inputs I0 and I1, and there are 2 input variables or 2 variables in the expression. So therefore I have to use one variable as the select input and the other variable as the input. I can use B as the select input and A as the input variable, or I can reverse. A can be used as select input and B can be used as input variable. Okay, it is our convenience. So now I have to fill the table. So there are two rows representing A bar and A. So now first row is filled with the values where A is 0. So that means the actually there are four entries. First entry represents the minterm 0, second entry represents minterm 2, third entry represents minterm 3, and minterm 2, and fourth entry represents minterm 3. So now out of these four entries, the minterm values 0, 1, 0 and 1 are filled in the first row, and the remaining two entries 2 and 3 are filled in the next row, that is second row. Actually in second row, actually we use the min terms for which a is equal to 1. Okay, I'll explain once again. So here we have taken two columns and two rows. So now we have two columns are I0 and I1, and two rows are A bar and A. Now we have to fill the table. The first row is filled with the min terms where A is equal to 0, and the second row is filled with the entries with min term entries where A is equal to 1. So now after this we have to highlight the boxes. So here in the if we observe the truth table, actually for the first minterm output is 0, and for the remaining three minterms outputs are equal to 1. So therefore we have to highlight 1, 2 and 3. So now we have to inspect each column. So in the first column 0 is not highlighted, but 2 is highlighted. So therefore, we have to write A below that. A means it is corresponding variable to minterm 2. So next in the second column, 1 is highlighted as well as 3 is highlighted. So here I have given, if both are highlighted, a 1 is written below that. So therefore, if here in this 1 is highlighted and 3 is highlighted, so therefore below that I have to write 1. So that means the entries are A and 1. Okay, so now we have to implement this table by using the multiplexer. So now the inputs I0 and I1 are connected to A and 1 respectively. That means I0 is connected to A and I1 is connected to logic 1 input. And the select input S is connected to the variable B. So this completes the implementation of OR gate. So now if you give S is equal to 0, that means B is equal to 0, then it will select A, that means I0. I0 is connected to A. If A becomes 0, output is 0. If A is 1, output is 1. And if B is equal to 1 means then I1 is selected, and naturally the output will be equal to 1. So which is verified in the truth table. See, the same procedure can be used for the implementation of the remaining gates. AND gate. So here I have given the definition, and here I have shown how to the same procedure is same, but you have to write this. Okay, first you have to write the truth table, and you have to write the table, and then you have to implement it using multiplexer. And since we are using two inputs for all gates except NOT gate, so therefore you have to use 2:1 mux. So this is for AND gate. This is for NOR gate. This is for NAND gate. For XOR gate, XNOR gate. Okay, procedure is same, but you should be careful while writing the truth table and writing the table. Okay, so this is for all other 6 gate, but except NOT gate. So NOT gate is having only one input and one output. So therefore, here we have to use only one variable. It has only one variable. So it is a simple. So here you need not write the extra table. Simply by seeing the truth table, we can implement it using the mux. See, the variable is used at the select input, and here for inputs, that is I0 is connected to logic 1 and I1 is grounded. So if A is equal to 0, output input is connected to 1 means output will become 1. If A is equal to 1 means I1 is selected, which is connected to ground. So therefore Y is equal to 0. So this functions like NOT gate. So then what is NOT gate? NOT gate is the logic circuit in which output is complement of the input. It has one input line and one output line. So if we give 0 as the input, then it produces 1 as the output. If we give 1 as the input, it produces 0 as the output. So therefore it can be implemented using the using 2:1 mux as shown in the slide. So now I think you are familiar how to implement logic gates using 2:1 mux. So if we are using more than two inputs, for example, 3 input OR gate or 3 input AND gate, then we have to use 4:1 mux for the implementation of the logic gate. So till now we studied the definition of multiplexer, that is in the last session, and now in this session I explained you about the applications. Multiplexer is used as data selector. It is used for data routing. It is used for waveform generation, for parallel to serial conversion. It is used as a frequency multiplexing system, and it is used as logic function generator. And main thing, it can be used for the implementation of Boolean expression and implementation of the logic gates. So this completes this session. Thank you.